that the Shapley Shubik method is a method for measuring the percentage of power that each player controls. So it's hard to tell how much power each player has from their votes, number of votes alone, because we saw examples where everyone can have a different number of votes, but then they all have equal power. It can also be, you can also have examples where everyone has very closely related numbers of votes, but their power is really different. All right, so we're going to use Shapley Shubik to measure the power of each player in this example. So Frontier High School has a school board made up of 3 members from Deerfield and then 2 each from Sunderland, Whately, and Conway. And for a motion to pass, a majority of the board has to vote yes. So our weighted voting notation is the square brackets. And the quota is what goes first before the colon. So how many total school board members are there? 9. Yep, 9. 3 plus 2 plus 2 plus 2. So 9 total members. And what would a majority of 9 be? 5. Yeah, so 5 is going to be our quota. So they told us that that's how you reach the quota. You need a majority. In this case, that's 5. All right, and then we put the weights of each player in descending order. So we'd have 3, 2, 2, 2. All right, and then to calculate the SSPI for each town, so we're going to have player 1 be Deerfield, and then player 2 will be Sunderland, player 3 will be Whately, and player 4 will be Conway. So we'll call this player 1, player 2, player 3, player 4. All right, so to figure out who the pivotal player is in each of these 24 sequential coalitions. So every player is in every sequential coalition. This is just 24 different ways that I can order them to rearrange the players. So this is Deerfield, Sunderland, Whately, Conway. And I just read from left to right, and whichever player gets you two or past the quota is the pivotal player. So we've got 3, 2, 2, and 2. So I put the numbers of votes just above to help me when I'm figuring out pivotal players. So who's pivotal in this case? Player 2. Because 3 plus 2 is 5, that gets me my quota. And then it's going to be the same here because that's also 3 and 2. And 3 and 2, 3 and 2, 3 and 2, 3 and 2. Because this whole first column, player 1 is first, and they have 3 votes. And everyone else has 2, so no matter who comes second, they're going to be pivotal. It'll get you to 5. All right, now this column is going to be a little different because player 2 is first in all of these. So this is all going to have 2s above them because player 2 has 2 votes. All right, and then player 1, they've got 3 votes. So in these two, player 1 is pivotal because 2 and 3 makes 5. But then in the next ones, player 3 only has 2 votes, so you have to go to the next player to get your 5 votes. And then same thing here. This makes sense? Coming back to you? Okay. So this is 2 and 3 makes 5. That's 2, 2, 1. There we go. There we go. All right, so now to calculate the SSPI, I have to count up how many times I circled each player. Okay, so player 1, player 2, player 3, All right, so how many times did I circle player 1? 12 times. And how many times did I circle anyone altogether? 24. And when you have 4 players, this will always be 24 because there are 24 sequential coalitions. All right, and then player 2, how many times did I circle player 2? 4. And player 3, I also circled 4 times. And player 4, 4 out of 24. So if I was going to reduce these fractions, this would be a half, and each of these would be 1/6, right? Divide the top and bottom by the same number. This one, divide the top and bottom by 12, and then these guys, you would divide the top and bottom by 4 to get a 1/6. But then I'm going to convert these to percentages, just because the next question is going to deal with percentages, and I want to be able to compare. So to change a fraction to a percent, can anyone remind me how to do that? Divided by the total. Yeah. So yeah, that's how you get the percentage of the populations. But what about these guys? This is like 12 over 24. How do I change that to a percent? Yes, how do you get that? Remind the people who forget, how do you do it? 12 divided by 24. So 0.5%. Multiply by 100. So you get 50%. Yeah. 50%. Okay. And then 1/6, we do the same thing. 1 divided by 6 times 100. And if I round that, it's like 17%. So I'm going to put a little squiggly equal sign. That means approximately. Like so I'm telling you I rounded it. Approximately 17%. So all of these will be approximately 17%. Okay, now if I add those up, they should add up to what? 100. They're going to be a little bit off. Why are they a little bit off? Because I rounded, yeah. So that's a reasonable thing. They should be close to 100%. Okay, so now we've had a controversial decision to change the high school's team name from the Redskins. It was in 1998. And after that decision, there were some complaints raised that the school board membership was not representative of the relative populations of the 4 towns. So some towns may have felt underrepresented on the school board. So the following table shows the population of each town in 2000. So we want to find each town's percentage of the total population. So I need to know the total population. When I add these up, I think I get 11,909. Okay. So now I want to find each town's percent of the population. So Deerfield, you do part to whole is a percentage, right? So Deerfield's part of the population to the whole population. So 4750 divided by 11,909 times 100. We'll just round that to 40%. Okay, so Deerfield controls it has 40% of the population, and they control 50% of the power. They have 40% of the population and 50% of the power. Are they going to go to the school board and complain that they are underrepresented? No, they are overrepresented, right? They have more power than they should have based on their population. Okay, so let's check Sunderland. So this would be 3,777 divided by 11,909. Times 100, just moves the decimal 2 to the right, and we get about 32%. Okay, so Sunderland, they have 32% of the population, and 17% of the power. Do they have anything to complain about? Yes. They have 32% of the population. Close to Deerfield, right? It's only 8% different from Deerfield, but they only have 17% of the power. So they are very underrepresented. Okay, so then let's do Whately and Conway. 1573 divided by 11,909. It's like 13%. About 15%. Okay, so Whately, 13% of the population, 17% of the power. Anything to complain about? Nope, they have more power than their population dictates. Same thing with Conway. They have a little more power than their population would dictate. So really, Sunderland is the town with something to complain about. Sunderland's the only town whose population is larger, and it is significantly larger than the percentage of power it controls. However, the argument can be made that a significant portion of the population of Sunderland is made up of transient residents, which means mostly UMass students, non-permanent residents, without children in the school system. What does this do to your answer to number 4? Does Sunderland still have a legitimate complaint? What do you think? Probably still do have a complaint. They should be or shouldn't be? Should not be included. Okay. Oh, I see. So you're saying that this number probably does not include the transient residents already. Oh, okay. Okay. Okay, good. That's good. So what if they are? What if we did count the UMass students in there, though? Should we say, well, then you really don't deserve 30% of the power, or should they still have 30% of the power, even though much of their population is temporary? Yep. That's a good idea. Yeah. So that is an important observation, is that why are we making this important decision without input from the people that it's really affecting? Yeah, good. Okay, another assumption that you made in answering questions 1 to 4. We assumed that all members from the same town would vote together when we calculated this power. We assumed that these 3 members from Deerfield are like one coalition, one block, one coalition that will always vote the same way. So if that's not true, then these power calculations don't really hold. But, all right, so I think we're going to move on from here. You can think about this last one on your own. And we're going to move on to a different method for how to calculate power. So this is a different power index, and it's called Banzaf. These are two YouTube videos on Shapley Shubik and Banzaf. They're really useful. You should watch them sometime if you have time, or if you're confused when you're doing your homework. They're really handy. All right, so last class we saw the Shapley Shubik power index as a way to measure distribution of power in a weighted voting system. Today we're going to see another way to measure power. All right, so in this method, we're going to have unordered coalitions. So in Shapley Shubik, every player was in every coalition. The only difference between the coalitions was the order. In this method, the order doesn't matter at all, right? So a coalition of player 1, player 2, and player 3, you can put them in any order and it's the same coalition. Just think of them like as a team. They're a team, the order that you put them in doesn't matter. And every player doesn't have to be in every coalition. So you can have just a team of 1 or a team of 2 instead of having every player on every coalition. So coalitions are sets of players. We use these curly brackets to describe them. With Shapley Shubik, we use those like arrow-looking brackets. And a coalition that does have every player on it is called the Grand Coalition. So a coalition is just a team of players. Any group of players that team up and say, we're going to be a coalition. We're a team. And a winning coalition is a coalition or a team that has enough votes to win. A coalition that can meet the quota. Any other coalition is called a losing coalition. All right, so in the last method we had pivotal players. In this method we have critical players. A member of a coalition is critical if the team or the coalition must have that player to meet the quota. If they leave and there are no longer enough votes to meet the quota, that player is critical. So it's possible to have more than one critical player in a coalition. All right, so here's an example. The Parliament of Icelandia has 200 members. The Red Party has 99 seats, the Blue Party has 98, and the Green Party has 3 seats. Decisions are made by a majority of vote, which means the quota is 101, because there's 200 members. Majority would be 101. So I want to write this weighted voting system in our standard notation. Question?
Oh, no.
Oh, okay. So we have the quota, and then we put the votes in descending order, 99, 98, 3. All right, so I'm going to fill in this table with winning coalitions. That's any team that can get the quota. So remember, we have red, blue, and green. Can any party reach the quota by themselves? No. Okay, so we have no winning single-person coalitions. Are there any 2-player coalitions that can meet the quota?
Yes.
Okay, who can team up to meet the quota? Red and green, blue and green, any red and blue. If they agree, then they meet the quota and form a winning coalition. So that's all the 2-player coalitions. Then obviously the 3-player coalition, if all 3 parties agree, red, blue, and green, is also a winning coalition. All right, so the weight of this coalition, red and green, add the weights of their votes. So that would be 99 and 3 is 102. And the weight of blue and green, 98 and 3 is 101. Red and blue is 197, and all 3 is 200. All right, so now we have to decide who is critical in each of these coalitions. So in the red and green coalition, think of them as a team. Red and green are a team. Together they have 102 votes. They can pass anything they want, right? If red says, I quit this team, and leaves green all alone, does green have enough votes to meet the quota? No. So that means red is critical, right? If red leaves, if red quits, green can't survive by itself. Yeah, same thing for green. If green quits, red doesn't have enough votes by itself. So green is also critical. So both players in this coalition are critical. Neither one can leave. If either one leaves, it's no longer a winning coalition. So critical players are both red and green here. Blue. Yes, same is true with blue and green. If either one leaves, we don't have 101 votes anymore. Both critical. Same with red and blue. If either one leaves, the one that's left no longer has enough votes to meet the quota. So both of those are critical. Now the 3-player coalition. This is a team with all 3 players. They formed a team. They're all going to vote together. If red leaves, red says, forget you guys, I'm out of here. That would just leave blue and green, right? Blue and green, do they have enough to meet the quota? Yes, that means that red is not critical. Red can leave and they'll be like, fine, leave. See if we care, right? So that makes red not critical. What if blue leaves? Red and green would be left together. They have enough votes to meet the quota by themselves, so that makes blue not critical either. And if green leaves, red and blue would be left together, and they also have enough votes to meet the quota by themselves, so they don't care if green leaves. Green is not critical. So in this coalition, none are critical. All right, so now we're going to define a precise way to measure the Banzhaf power index. Make a list of all possible coalitions and determine which ones are winning coalitions. So we actually skipped the all possible coalitions here, and we only wrote down the winners. That's fine. You can do it either way. You can write down every possible team and then identify which ones are winning teams, or you can just systematically try to come up with the winning teams. Find the critical players in each coalition. Did that. And then to find the Banzhaf power index, count the total number of times each player is critical. Then divide by the total number of times all players are critical. So it's very much like Shapley Shubik, right? How many times did you circle each player? Divide by the total number of circles. So if I calculate my power index for Icelandia, how many times is red critical? I circled red twice. Once here and once here. So I'm just looking at all my circles. Red got circled twice. How many total circles do I have up here? 6. So 2 out of 6. How many times is blue critical? 2. Also 2 out of 6. And green? 2. So my Banzhaf power index is 2 out of 6, 2 out of 6, 2 out of 6. That is a third, a third, a third. Is that surprising to you? They all have equal power? When their vote numbers are 99, 98, and 3, and it turns out they all have equal power. This is why we need a mathematical way of measuring power, because this is misleading. This makes it look like the Green Party has very little power, when in fact they have power equal to the other two parties. This procedure, as well as SSPI, is on a reference sheet on page 7 and 8 of your packet, and you can use that sheet on your test. Just show it to you. So this is Shapley Shubik and Banzaf. Okay, so in a simplified version of the Celtics draft system, the head coach, who we're going to call player 1, gets 4 votes. The general manager, player 2, gets 3 votes. The director of scouting, player 3, has 2 votes, and the team psychiatrist, player 4, has 1 vote. That's 10 votes total. Of the 10 votes, a simple majority, which is how many? 6, is required for a yes vote for a player to be drafted. So I want you to write down the system mathematically and find the Banzaf power distribution. So the first number in this notation is the quota. Okay, so very common mistake is to put the total number of votes, but it's the quota that goes here. So you have to add up the total, 4 plus 3 plus 2 plus 1, and you get 10. And then they tell you that a majority is required to pass to vote on a player to be drafted, and a majority of 10 would be 6. Then we put the votes in descending order. 4, 3, 2, 1. All right, so to find the Banzaf power distribution, we have to think of all the winning coalitions. So we want to do this as systematically as possible to try to not miss one, because this is the hardest part of this method, is writing down all the winning coalitions. Okay, so 1-player coalitions, 2-player, 3-player, and 4-player. So I do this to try to organize my work. Are there any 1-player teams? Does anyone have 6 votes by themselves? No. Okay. Are there any 2-player teams that can reach 6 votes? Player 1 and player 2, the 4 and the 3 together. And player 1 and player 3, the 4 and the 2. Make 6. Okay, so those are there any others? No, there's no other team of 2 that can reach 6 votes. So then we move on to teams that have 3 players on them that can get 6 votes. So I'm going to do this again systematically. I'm going to start with player 1. Teams that have player 1 on them that can get 6 votes. So I could do 2 and 3. Player 1, player 2, player 3, they have 9 votes. Okay. Then, since I'm already working with player 1, player 2, I could also do player 1, player 2, player 4. They would have 8 votes. So when I'm trying to write these down systematically, I'm doing all the 3 players that start with player 1, player 2. Are there any other ways that I can write player 1, player 2, somebody else? No, because there were only 3 and 4 are the only 2 left. All right, so now instead of player 1, player 2, let's go player 1, player 3. Okay. I can't put player 2 next because player 1, player 3, player 2 is the same as player 1, player 2, player 3, because order doesn't matter here. So I could put player 4 here. 1, 3, and 4, that's 4, 5, 6, 7, so they have the quota. Are there any other 3-player teams that start with player 1? No. So I move on to teams that start with player 2, and the only one would be player 2, player 3, player 4. And then that's it. I can't start with player 3 because anything that I start with player 3 is going to have to put down other, it's just going to be a repeat of something I've already written, just in a different order. that make sense? Okay. These are all the possible 3-player teams. It happens that they're all winning in this case. And if you go back and look at page 8, these are all the coalitions with 4 players, right? So we have all the single coalitions, all the 2-player coalitions, all the 3-player coalitions, and the grand coalition. So if you're ever stuck, you can just go look here and you have all the coalitions and you can just determine which of these are winners. So this can be a big help in your homework if you're having trouble coming up with the winning coalitions. All right, and then we have the 4-player coalition, player 1, player 2, player 3, player 4. All right, so these are all the winning coalitions. Now I have to figure out who is critical in each of these coalitions. So it helps me to write the vote count on top of each of these. So this is 4 and 3, 4 and 2, 4, 3, 2, 4, 3, 1, 4, 2, 1, 3, 2, 1. Okay. So I have the vote count on top of each player. And then I have to ask myself separately for each coalition, for each player, if that player leaves the coalition, does the coalition care, right? If the coalition's like, no, don't go, we need you, that makes them critical. If they're like, whatever, we can still pass a motion, that makes them not critical. So if player 1 leaves, what does player 2 say? No, don't leave, I need you. Right, yeah, so they're both critical, right? If either one leaves, the other player doesn't have enough votes to pass the motion. All right, let's look at the 3-player coalition 4-3-2. If player 1 leaves, player 2 and 3 still have 5 votes. So they're like, no, don't leave, right? You're critical. If player 2 were to leave, player 1 and player 3 would have 6 votes. So they'd be like, fine, go. We don't care. So player 2 is not critical. And then player 3, if they leave, player 1 and player 2 would still have 7 votes. They don't care. So player 3 can leave. They're not critical. Okay, 1, 2, and 4. Who's critical here? 1 is definitely critical because then the last 2 only have 4 votes together. What if player 2 leaves? 2 is critical because the 4 and the 1 are left, and that's only 5. And if player 4 leaves, we don't care, right? Because the other 2 players still have 7 votes, so they're not critical. All right, player 1, they cannot leave. Player 3 cannot leave. Player 4 can go, no problem. All right, if player 2 leaves, there's not enough. If player 3 leaves, not enough. Player 1 leaves, not enough. All of them are critical in that one. All right, and then in the 4-player coalition, who's critical? No one, right? So even if player 1, who has the most votes, even if they leave, the remaining 3 have 6 votes. So no one's critical there. All right, so now I just have to calculate my fractions or percentages. We'll do that over here. So player 1, player 2. Okay, so my total number of circles is 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's my denominator. And then of those 12 circles, how many are player 1s? 5. So 1, 2, 1, 2, 3, 4, 5. And how many are player 2? 3. And how many are player 3? 1. Yeah, and how many are player 4? 1. So if I add up my numerators, 5 plus 3 plus 3 plus 1, what do I get? 12. For 12 out of 12 circles, right? So when you add up all your numerators, you should get the denominator. Or you can say if I add up all these fractions, I should get 1 for 100% of the power. So then I would reduce these or change them to percentages. 5 out of 12 is reduced. 3 out of 12, that's a fourth. And 1 out of 12, that's as reduced as it can get. So 5 out of 12 is a little more than half the power goes to the head coach. Oh, sorry, a little less than half the power, yeah. And then a quarter of the power each goes to, who was it? The GM and the director of scouting. And then the team psychiatrist has just a little sliver of the power, 1/12 of the pie. So who has the most power? Head coach. The least power, that would be the psychiatrist. Psychiatrist. And any surprising results? You weren't surprised that the player 2 and player 3, that the GM and the head scout have equal power? Different numbers of votes, but equal power? You're over the point where you're surprised by things now. Because I surprise you every day, right? Yes. Yeah, that's a good analysis, yeah. 3 plus 2 is 5. You need 6 to get the quota, so they're always going to like sort of bring you a little short. Yeah. So we have some yes and some no. So computing the Banzhaf power index and the Shapley Shubik power index becomes very time consuming and tedious when we increase the number of players, right? But you can let technology help you do some of the tedious stuff. So let's use the following web page to confirm the BPI for the Celtics example. And then we'll do the King example that we talked about last class. Okay. So before I let you start on the activity for today, I want you to take note that part of your homework, which is listed in Other Things to Do section, asks you to go to page 3 of this document and cut out the long rectangle that has 2 copies of the alphabet and the short rectangle that has 1 copy of the alphabet, and bring them with you next class. So in under the learning objectives, okay, your homework is the My Math Lab assignment, right? Which was supposed to be due today, but I'm extending it till next week. And then also under Other Things to Do, finish up project 1. I'm going to collect that on Thursday, unless you have it today, and I'll take it today. And then other thing is go to page 3 of this document, and there are some rectangles with the alphabet that I want you to cut out and bring to class. Yes, these guys. So I want you to cut out these. One has the alphabet twice, and one has the alphabet once. So cut out these 2 rectangles, the long one and the skinny one. Just the length. You don't have to cut out each individual letter. Just the full rectangle. Yeah, that one. Just one is fine. Just one is fine.